Let me move a little Windows and share the screen. Okay, now I guess you see my screen. And we can start here. Wow. Okay, before going on, do you have questions from yesterday? Or till here is all clear? Great, sounds good. Okay, so if you remember, we just solved different...
I have a question
regarding
regarding
yes.
this. I have still a little bit confusion about we are calculating the amplification and also with a movement of the buildings, but based on the mechanism of waves that for which we know the source parameters. Like we are making the source parameter very near to the building. So how can we compare it with the waves, the velocity of the waves that source is arbitrary and not very near to the building? So I have a little bit confusion about this.
So I'm not sure if I correctly understood. You mean when we are talking about of interferometry in this sense?
Yeah, the previous yesterday's lecture in which we were making the experiments related to the movement of the buildings, but using the some experiments. Yeah, these were in this. So I was confused. Do we expect the same movement of the buildings when earthquake waves passing through it?
No. Okay, so this is what we are studying. It's for small oscillation, unless you are, and we will see today, also studying recordings of large earthquakes. But of course, during strong motion, the behavior of a structure will change. So these studies are able to show you what is the starting behavior of a structure. So under small, let's say, oscillation, under a small load, when the motion will become much larger, then the behavior of the structure also will change. But as I said yesterday, for modeling correctly a structure, you need also good starting parameters. And at least these measurements allow you to fix the good parameters at the beginning of a simulation when the shaking is small. And then how this will evolve and how the behavior of the building will change will depend, of course, also on these starting parameters and how they degrade with time. So even if they cannot represent fully the behavior of a structure, they are still significant to fix correctly some of the parameters necessary for the simulation. I have also to admit that recently we are trying to make some very simple assumption just to check in the first order. We don't want to simulate the dynamic behavior of a structure, but we want just to see if the structure could have overstepped during shaking some level for which it could be in a status of damage, let's say. We were very skeptical till a few years ago about this possibility to make a very simple simulation of a structure and directly in the field to get these values, exactly because of all these complications. But we are publishing now a paper and we are making also some other analyses that are showing that at least for the first level of damage, just to understand if this structure could have been damaged during the shaking, they can be sufficient. And a few years ago, it was not really clear this. So it's a good starting point, okay?
Yeah.
So now we come back to the interferometry that, as I said, you can use it in boreholes, you can use it in buildings, you can use it, as we have seen, also to study the crustal structure from earthquake or from seismic noise. And there are mainly two approaches when we look at interferometry, and especially looking in the analysis of data. One is to use the cross correlation, and one is mainly to use the deconvolution. In reality, they are very closely related, in the sense that if you look at this deconvolution, where half here is this term, which is multiplied for the other recording. So this is the recording, for example, that we use in one point. This is the reference point, and this is the deconvolution. When I calculate the deconvolution, generally, I go from this equation through this equation because I need to consider also a certain water level. So I don't want that my denominator is becoming too small, because this could affect the ratio between the two spectra, and I could have some artifacts due to numerical problems or numerical noise in my spectra. If you look then to the denominator that would become the spectrum of this for the complex conjugate of the other spectrum, you immediately recognize a term which is equal to the cross correlation of the two signals. What is different is that you have a sort of, let's say, normalization for each frequency that depends on the power spectrum of each frequency at the reference station. What is the advantage in terms of the convolution, in my opinion, is that in this way you can remove the source effect, while with the cross correlation, the source effect is still in your signal. So in terms of amplitude, your green function will be proportional to the results of the convolution will be proportional to the green function, while with the convolution you should be able to obtain a good estimation of the green function, even if, of course, band limited, because we have only a certain band, like you can see here, that we can exploit with our spectra. And this depends on our sampling rate, it depends on the quality of the signal and signal to noise ratio in certain bands, and so on. So this can be, of course, applied, for example, if we have a sensor on the roof of a building, or can be on the top of the surface of the ground. You can have a recording in the bedrock, or can be, let's say, in the basement of a building, and you can apply this technique. For example, if you use the roof as a reference, you will obtain two signals like we have seen. One is describing the acausal part of the propagation, so it could be seen as a sort of signal propagating from the bottom to the top, and then the part of the signal that from the top is sent back, let's say, in the ground or through the building as a positive time. Or you can see it also, it's like if you have a hammer on the roof and you are just sending the signal down to the ground. In the spectra, here are already indicated the fact that having downgoing waves, the waves that are propagating down, can create a negative interference at particular frequencies, and this negative interference is generating spectral holes in the recordings, exactly like we have seen, if you remember, for the Borel recordings. So if we try to describe the propagation now of waves in a very simple model, so we can assume that we have a sensor which is in underground, or can be, let's say, at the bottom of our building, and a sensor at the surface, or can be, let's say, the building, the roof of a building. So we can describe the ground motion, assuming that the medium here is homogeneous, in a very simple way. So the recording that I have here in the ground will depend on the input motion that we have here. So we are not discussing in terms of time series, but this is the Fourier transform of the recording here. So will depend on the incoming wave coming below that we call x0 omega. And then what I record here will be also the wave that is going up and come down. So I can describe this as the wave that is recorded at the surface, epsilon of omega. We know that this wave is as an amplitude. If we consider shear waves, no, we are considering shear waves with vertical propagation as an amplitude which is doubled. So what I'm recording then here in the underground will be the wave that was here at the time tau before, so the time that is needed from the wave to go from here to here, with an amplitude that has to be divided for 2. So my recording here will depend from the input from below and will depend from what reach the surface and come down with half of this amplitude and with a time of propagation tau that depends on the thickness and on the velocity here. And what I'm recording at the surface, it's simply what is coming, the incoming wave field that is propagating to the top, double is amplitude for the free surface effects, and it is delayed with respect to the incoming wave field here of the amount of time tau, and therefore this shifted, let's say, as a frequency, as a shifted of a phase that will depend on omega tau that we have here. So we can describe this very simply in a homogeneous medium. So now what I can do, I can calculate the transfer function, so the function that is describing the propagation, for example, from the top to the bottom. And in this case, this would be identical to the ratio between the spectrum epsilon omega t and x of epsilon of omega and x of omega. I can also decide to do something different. I can calculate also the ratio between x of omega and epsilon of omega, considering the reference, in this case of the ground motion, the recording at the surface. So if I do this, so if I calculate the ratio between the recording in the borehole and the recording on the at the surface, I immediately see that what I obtain is a function that has a constant coefficient 0.5 that is related to the fact that, as we said many times, the ground motion at the surface is larger due to the free surface effect. But that has also an interesting term that we see is describing the upgoing propagation here with the terms minus tau. This is just a question of definition. And then another term that is describing the downgoing propagation for the positive time. So if I calculate the ratio, so my interferometry or my deconvolution between the sensor in depth and the sensor which are at the surface, I can distinguish two waves propagating up in the upgoing in the downgoing sense. Things could be a little bit more complicated if I would take the ratio between x of over epsilon over x. This will complicate a little bit the vision of what is happening. So if this is an example of the recordings in the Millikan library. This is a typical example that you will find in many books. So these are recordings from the basement of a building to the upper floor of a building, which is the 10th floor. You immediately see that the recording on the basement is mainly made of a small amplitude shaking and mainly high frequency. you can immediately see that the shaking is increasing while we move up to the building, and then you immediately see low frequency oscillation, nearly with the same frequency, that are becoming more and more clear when we go in the upper floor of a structure. And this is the results of the application of the deconvolution to these recordings. In the case on the top, the reference station was used the one in the bottom. In the case of the bottom, we calculate exactly the response, considering as the reference, like in this case, the one which the station which is on the top of the building. You see that the results look very different. In the case we are using the station in the bottom as a reference, it's like if we have a pulse or a source that is generated in the basement, the waves start to propagate up in the structure. When they reach the top, due to the interference, the building starts oscillating. So you have the first part of propagation here, and then you clearly see the large oscillation of the structure due to the induced shaking of the building. When we use the reference as the top, all these oscillations are removed. We only identify the part of ground motion related to the upgoing and downgoing propagation of waves inside the buildings. What you see here, it's very similar to what you could have also in the underground, for example. So depending on the choice that you are doing for the reference station, the results can be quite different and can highlight different characteristics of a structure and of a wave propagation. So you can clearly see here again, if we have a deconvolution on the top, this is more or less the autocorrelation of a signal, like we have seen before. And it's more similar to a peak. And then you can see the acausal part and the causal part of the propagation of the buildings, of the waves inside the building. And you can also look at the velocity. If we know the distance between the different floors, you can measure the arrival time, and you can see the upgoing and downgoing wave, and also measure the velocity at which they propagate. If we come back to the analysis using the station in the basement as the reference, like we said before, we can identify two different parts in our green function. The first part is mainly related to the waves traveling up in the building, reaching the top and going down, propagating down in the structure, and then repropagating after having changed the sign of the impulse, because at the bottom, when they found an impedance contrast, which is large, then the polarity of the waves is changing. Well, then here we have a part where we have an oscillation that is strongly related to the normal modes of the structure. You see that all these oscillations are in phase. So this large oscillation have the same frequency, different amplitude while we are going up, and are all in phase. So this is strongly related to the first mode of oscillation of a structure that we have seen yesterday. Exactly this one. So we go up, the amplitude of shaking is increasing, but the frequency is always the same. It's independent on the position inside the structure. So this was already quite clear in the earthquake recordings. In this case, you see the first part where you have propagation, and the second part where you have the oscillation of the structure, but of course can become more clear after the deconvolution, because we clean, let's say, it's like if we clean our recordings by the effect of the source, that is not a flat spectrum, so can give emphasis to some particular frequencies due to the how strong is the source, and we keep only the information on the propagation terms. So in this way, we can better study the propagation in the structure. And so we see, for example, here clearly the upgoing waves with a positive sign, the first downgoing waves, because when it reaches the surface, will not change the polarity. So the waves will propagate down with the same polarity. We assume it's positive in this case, if it's an up. Then the wave reach the basement. Due to the contrast in the basement, the wave is changing the polarity and is propagating up to the roof again. Reach the roof, and again, it's propagating down with the same polarity, which is a minus, and here it changes again and becomes a plus, and so on, until the effect of the damping of the attenuation is masking the propagation of the waves. As I said, this you can see it in a building, but very similar situation. You can imagine if you have a sensor at the surface in a borehole and a sensor just on the bedrock inside the borehole, like we have seen for side effects. If we look then at this oscillation that we have later, we can immediately measure the period of this oscillation, and we know that the period is related in some way to the height of a building that we can know, for example, and the velocity also propagation of waves. So we can estimate the resonance frequency of the structure also directly in this way, or we can confirm it. So this game can be done also using not only earthquake, but also noise recordings. So if you use noise recordings, it means that we will not have only an input of shaking at the base of a building, but noise can be generated also inside of a building. For example, people moving or whatever machine is activated and so on. Therefore, when we apply the same spectral ratio, let's say with the convolution of the shaking of different instruments installed in the building with a one at the basement, differently from what we get from earthquakes, where we have only a causal part of the signal, when we have noise, we will see a causal and a acausal part of the signal. You see they are symmetric. Also in this case, it's very easy to estimate the upgoing wave propagating in the building that then is very strongly attenuated, as well as the other modal related oscillation in the structure. So even here we can separate the contribution of waves propagating inside the structure from the oscillation of the structure itself. So,
yeah, hello.
Yeah.
Can you go back in the slide?
Yes.
Again. You said that we will have a change in a polarity.
Yes.
I don't understand why.
Because when you have a change in the impedance contrast, then the polarity of the signal due to the change of stiffness will change. So what is, it's normal in seismic reflection. So the reflection at the surface, you are going from a medium with a higher impedance to a smaller impedance, will give you a reflection with the same sign. When you have a change from, let's say in this case, a lower impedance to a higher impedance, then the reflected wave will start with a different polarity. This is generally what you expect also from seismic and from the wave propagation due to the tension and the stress generated in the material. So it's nothing strange. In this case, it's only mean that here we had at the basement a impedance contrast between a smaller impedance to a larger impedance of the material. Okay.
Okay. Thank you.
So since you have also this clean function, and here, for example, you see to the left the one calculated with respect to the top of a building. You can filter them also in a different frequency band if you want to see some details for these frequencies. But okay, the main point is that using the upgoing and the downgoing wave and the travel time that it takes to them to propagate, you can easily estimate the velocity in each different, let's say, interval of height of a structure. So you can see if the velocity in the structure is changing due to the structure itself. Why you want to do it? Because of course, in case of large earthquake, like we will see, changes in the velocity that you observe here can be related to damage to the structure. So a damaged structure will change the velocity at which the waves are propagating, and generally it's becoming smaller. Similarly, if we take also the slope of the convolved wave field that you have seen before in a logarithmic scale, one can prove that this is proportional to the quality factor or to the damping of the building itself. So in this way, at least for a small level of shaking, it is possible to get information about the velocity of propagation of waves inside the structure and also about the damping. Similar operation, again, I want to stress, can be done if you have a borehole where you have an instrument at the surface and many instruments at different depth. You can estimate the velocity of propagation of waves in the borehole, the characteristics, how they are changing over time and depending on the input shaking, so if you have non-linearity, but also you can have, through different methods, some information about the quality factor. Important point, as usual, the velocity can be quite well constrained. Much larger uncertainties, you can use also quite complicated methods to obtain Q. Much larger uncertainties are affecting the damping estimation, especially in borehole data. In the buildings, probably a little bit less. This is if you remember yesterday, we showed the example of the AEPA hospital. We studied it a few years ago with the data we had. So since we're having ambient vibration recordings and also a few earthquake recordings, we could make also a comparison of the results obtained by seismic noise and earthquakes. Unfortunately, the recording of earthquakes were not as well distributed like the recording for noise. We had much more sensors in that case. And but in general, the results for small induced ground motion by the earthquake, there was some reasonable agreement or quite good agreement between the results obtained from seismic noise and from earthquakes in terms especially of estimation of the velocity of propagation of waves in the same interval of floors. This is another example in a much taller building. So in taller buildings, of course, it's easier to estimate their characteristic because the oscillation is large, the time of propagation of waves is longer, so we can better separate the impulse related to the upgoing and downgoing waves. But when the buildings are tall, doesn't mean that they are simple. They can be also quite complicated, like also the underground, where you have a change of stiffness at different depth. So this is the example of the convolution of the building in Istanbul that I showed you yesterday, where we were also making this active source experiment. And one interesting point that we noticed was that we had here a clear propagation of going and downgoing wave, but we could also find some signals starting from the 13 floors having a clear change of polarities in the X, but also in the Y direction, something that we really didn't expect at the time, and that was, of course, consistent with some characteristic of change of the characteristic of the building at that level. We also made analysis using seismic noise. In this case, these are the results using the station at the basement as a reference. Once again, you see, when we use seismic noise, even if a station is in the basement, we have symmetrical results, both in the X and the Y direction of the structure. And we could identify, for example, a clear upgoing wave reaching the top here in violet, coming down, and then becoming much smaller later, while we could clearly observe different oscillation, also with different frequencies for different height inside the structure. So higher modes were overlapping with the fundamental mode. So while in the Millikan library, the fundamental mode was quite clearly obtained and was dominating, here you can clearly see that there is an overimposition of different modes with different frequencies that are becoming more or less important depending on the height inside the building. And if you see this effect, we have this clear change of polarity of signals from the roof till the 11, 12 floor. That was indicating a complete change of the characteristic of a building from the 18 floors in the uppermost part of the structure. So if we come back to another kind of building, this is the building that we were analyzing in Bishkek and we have seen yesterday with sensors positioned in different places of a structure. Yes.
I have a question in the slide before.
Yes.
Before, like yes. Where you saw the one before.
Before?
One more.
Yes.
Yeah. So here, like we see a change from 13th floor.
Yes.
So why is it like a usual or it's only
no?
This
it
building?
depends. It depends on the structure, particular structure of this building. As I said, in general, we didn't observe it, but there is a clear change in the design of the building from what you have till the 11th floor and the top that you don't see here, but we learn it later. And this is what is changing then or what is determining this kind of behavior. And we discover it only after that we made measurements there. So this is really particular of this structure. And okay, this is the same that you have done, is a similar kind of analysis where depending on the points, you can also see that you have different propagation of the wave velocity. You see that the propagation from the bottom to the top, it takes a bit more time when you look at the X direction than the Y direction. And this is important also to estimate characteristic or changes in the characteristic of the structure depending on the position in the building. I remember you that point A is here, this is the point B, and this is the point C. So you can identify also some changes in the characteristic of the structure. So if you plot all these estimated time versus the height, you can calculate also the velocity at which the waves are propagating in the structure, and to use this velocity as a reference, maybe if you have instruments that are installed in a permanent way in the structure, this could be a sort of reference for later identifying possible damages to the structure itself. In this case, you see we estimate in the different direction of the buildings, different velocity of propagation. In the X direction, generally, we have a smaller velocity of propagation of waves, which anyway change also significantly, so more than what we expect from standard errors in the different position. And this is because the structure is different in different part of the structure, and it's larger, but a little bit more homogeneous in the Y direction of a building. So, as I mentioned, okay, these are measurements that we can do just to fix some of the parameters, for example, the stiffness, rigidity, that are important for also our numerical simulation. One question is, can we also use this approach for making some damage detection? And generally, we have 3 levels of detection. General one that we can call level 1 is we can estimate a change in the total travel time. And the change in the total travel time, so from the propagation of waves from the bottom to the top of a structure, is generally related to the fundamental frequency of the structure. So if the damage is enough large to be seen all over when smeared over this travel time, we can have an information about it. Of course, we don't know exactly probably how big it is because it's smeared over the whole path. And we can also, we don't know also where to locate it. If we then start looking at, if we have more sensor and we look at the changes in travel time between different floors or block, okay, the estimations start to be more local. And finally, if we check also how much are the changes in velocities, depending on the changing of stiffness, then we can arrive to a more defined estimation of a damage to the structure during an earthquake. So if we look at, for example, of global changes. So if we look at the recordings, these are recordings taken from a building that I think it's always the Millikan Library. You see, depending on the earthquake, the fundamental frequency of the structure, here you have the fundamental frequency of the structure, which is indicated F1, and the fundamental frequency of the whole system, so structure plus soil. You see that it can vary during the strong phase of shaking. So it means the building is damaged. So being damaged, the fundamental frequency generally is diminishing. Then you see that the building was repaired, and you have many other earthquakes that happened, but that were not significantly changing during the shaking, for example, of the resonance frequency of the structure. Then, during the Nordridge earthquake, when the shaking was again large, at the beginning there is already a decrease of the frequency, and the large decrease, and the frequency is not retrieved anymore because the building had been damaged again. So already looking at the changes in the frequency of the structure, we can have some information about possible damage to the structure itself. If you want to see local changes, this is the example of recordings at different levels in the structure. And this was a building, the ICS, that was damaged by the Imperial Valley earthquake of 1979. One can check at the changes, for example, on the characteristics of the recordings through the different floors. And if you use the interferometry, you can calculate the convolution between the different floors, and you can see how the deconvolution, for example, is changing for different windows of the seismogram. So it means, if I go back a little bit, I take different windows of the seismogram, and for each window, I calculate the deconvolution. In the small windows, when the shaking will be still small, I expect that my upgoing and downgoing waves propagates always with the same velocity. But when I enter in the strong motion phases, so later, the results of the deconvolution can be different and can show some differences. So for example, here you see at the beginning between these two floors, the travel time was relatively, between the upgoing and downgoing wave, was relatively short. In the last window, so after 13 to 23 seconds, when the large shaking already arrived, if I recalculate the green function there, the travel time is becoming larger. And this is related to a change from the travel time to a change in velocity. And the change in velocity is related to the change in stiffness, let's say, shear modulus of the material. So this is a good way also to check if a possible damage happened to the structure. Why you have to do it on different windows? You have to do it because anyway, the convolution operation that we assumed before, it's a linear filter. So we assume that the filter all over the time series, or my seismogram, the time analyzing, is constant. So the characteristic of my filter, of my propagation, from the bottom to the top, is always the same during all the shaking, all the window of signal that I'm analyzing. If this is not true, okay, the operation should not be valid. That's why I select many smaller windows on which I do the operation, and I assume that in each small window, everything is linear. But from one window to another, the filter, let's say, my transfer function can change. So I do some sort of assumption of linearity in each single window of time that I'm using. When I change the window of time, the green function can also change. So, and this is true, especially if we have a strong shaking. That was one of the questions at the beginning. So if we have strong shaking, we know that no linearity will happen. So to do this, and to avoid many windows and so on, we decided, for example, to make use of what is called a Stockwell transfer. The Stockwell transfer is just calculating spectra, like many spectra, in different time windows with different resolution depending on the frequency and time. And so directly on this spectra from the Stockwell function is possible to calculate the deconvolution. So we can obtain, we can estimate the green function, the propagation function at each instant of time where we measure. So we can do this, and we can, of course, measure then what is the velocity of propagation for different instant of time, and also measuring what is the frequency, because the frequency, we know it's related to the velocity. Of course, h in this case is the height of the building that we know. So this is an example of application. If we select from the analysis just windows taken at different time, so each color in these plots represent the results obtained for windows in this interval of time. The black window is the window, let's say, just at the very beginning of shaking. So it's a sort of our reference because the shaking is small. Then we have a window at nearly 50 seconds. So when we have a very large shaking, which is this blue window, and then we enter in the coda of the seismogram, and then in the deep coda with the red windows. So what we observe in this building, this was one of the buildings that we analyzed together with Giovanna Pianese and Roberto Paolucci from Milan. What we were observing is that not immediately, but especially after some times, probably also due to the duration of shaking, the building that was damaged by the 1995 event start to show clearly a change in the green function. You see that the time passing between the upgoing and the downgoing wave is increasing when I enter in the coda of a seismogram. So what it means that when I enter in this later phase, the building is damaged and the waves propagating in the buildings takes more time. Then the building was also retrofitted. So at this time, for example, during this earthquake in 95, one could estimate some increase of delay of time. For example, from the first window to the last window, there is an increase of 36%, which is a large amount in the transverse component of the building, and 39%, which is again very large due to the damage in the longitudinal component of the building. If we look at the event of 1995, looking a little bit at the recordings that were taken in the structure on the longitudinal and transverse component, we estimated the fixed base frequency, so only the frequency, let's say in this way, for the building itself without accounting for the coupling with the soil. And it was very clear that when the large shaking was starting, there was a clear change in the frequency of the building, and this clear change was mainly related to the arrival of these two waves packets that were generating a clear diminishing of the resonance frequency. On the transverse component, this was much less evident. So mainly in the longitudinal component, we observed large damage in the Jalapa building in Mexico City. Then there was another earthquake, if we think 1993, that was anyway generating interesting PGA of 8 centimeters per second square. But this you immediately see it's a much smaller level of shaking. Even if we take windows in different part of a seismogram, we observe that the green function are more or less stable. So there is nearly no change in the behavior of a building, and this is because this smaller earthquake did not generate damage in the structure. Only very small amount of changes are observed, 4 and 9%. And if we do the same, we can clearly see that there is a very small change in the resonance frequency, in the longitudinal, and in the transverse component of motion. So in this case, we know that the earthquake was not generating damage to the structure. And it's confirmed also by the observation that we had. So till now, we mainly focus on the effect of the propagation of waves and so either in the soil or in the building. But as I mentioned, this system is not decoupled. So the building is now part of the soil. And so when the shaking is affecting the structure is reacting like we have seen and is releasing also waves back in the soil. So we will focus also in studying how much is this soil structure interaction, how important it can be, and if this can be significant for the level of shaking that can be observed, let's say, around the building. There has been example in the past that were trying to study the effect on the shaking due to the presence of buildings. So one of the examples is already was done 10 years ago after the Molise earthquake. And it was shown, for example, that one of the two buildings here represented could have suffered larger damage also due to the interference related to the presence of the other structure. Other studies show that for some distribution of building structure over especially sedimentary basin, locally the presence of the buildings could increase or decrease the level of shaking. So it means if you have a building in an area where the shaking is decreased, you probably, for the same amount of vulnerability, let's say, of a structure, you will suffer less damage. If you are in an area where the shaking can increase due to the presence of a building, for the same vulnerability, you could have more damage to the structure. So if we could study this before and know it before, maybe in this way we could also try to mitigate a little bit this kind of effect. And that's also part of the aim of some work package, for example, of the Urbesis project. Many of you are part of Urbesis, so you know that this is one of the challenging tasks that is in Urbesis. Of course, we do not expect that Urbesis will solve all this problem, but it's moving exactly in this direction. So one of the first attempts we have done already a few years ago was to say, okay, if we could have not only building with sensors which are installed, but nearby also having borers with sensor in the underground, at least we could start studying if we can recognize this effect of coupling between the building structure and the soil directly in the field, and not only with numerical simulation that by definition are always based on simple models. Even if we try, of course, to make models much more and more complicated, more realistic. So the idea was to see if I have waves arriving there, buildings are releasing back energy. Can I see this energy, how important it is in terms of determining the shaking? How much can influence the nearby building? So we started this in a few places. And you have seen already this example. This is an example that is showing, okay, I have waves coming. There are some reflection, but when the waves is arriving in the building, depending on the impedance contrast, some of the energy can be trapped, like you see here, and the color change means polarity change, exactly like I showed you before, and then you have a continuous propagation of waves. This is just an example for a building in Bishkek where we had many instruments here and different instruments in the borough. But how to recognize this part of energy that is going down? How can we see it in real recordings? So we came back again to the interferometric approach. So, okay, we can check how much it is if we can study what is its, for this particular energy sent back, let's say, by the building, if we can estimate its propagation function, its green function. In this case, we can assume that the soil is our first layer, and the second layer can be assumed on the building, and we study mainly only vertical propagation of waves, just to keep it simple. Between these two layers, so between, for example, the building and the soil, there could be a certain reflection coefficient that, of course, depends on the impedance contrast between the building and the soil. And this impedance contrast can be different depending on the kind of soil, but also on the characteristic of a building itself. So if we should now describe the wave propagation, the things are slightly more complicated than before. And if we complicate further with many layers, probably we cannot follow an analytical solution anymore. We have to rely on numerical solutions. But very simply what we can say, okay, the recording that I have at a certain depth will depend again on the incoming wave from below, from the waves which are reflected at the surface. No, this could be the interface between the surface and then the building. And the waves which are reflected at the free surface. Here, the free surface, we assume it's the roof, for example, of the building. So this wave is just the incoming wave. This wave here is just the reflected at the interface, and how much is reflected depends on the reflection coefficient, so on this impedance contrast, and will be shifted with respect to the input of a travel time that we call tau2, that depends on the propagation from here to here. So the times to go up and to go down. Plus, we have the waves that goes up, reach the surface, so it's identical to what we recorded at the surface divided 2, once again. Only one part is, let's say, going up, and then, because it's the part that is not reflected at this boundary, so it's the part that is transmitted here, and then it will take a time that depends on the propagation in the first layer, tau1, and the propagation in the second layer, tau2. So we have input, reflected, and wave transmitted, reflected, and again transmitted down to the sensor. So we have these three components that are recorded at our sensor in the underground. What is recorded at the surface? Okay, at the surface, I will have the input shaking that is transmitted here, this term, that reach then the surface, and therefore it's multiplied for a factor 2, and how much time it takes for this wave that was here to reach the surface. Okay, it will take the time tau1 to propagate in the first layer, plus the time tau2 to propagate in the second layer. Is this all? No, it's not all, because I will have also, since there is an impedance contrast here, I will have a wave that I recorded at 2 times tau1, so for the propagation here, that is coming up again at the surface, and it's reflected at this interface here with a reflection coefficient that depends on the impedance contrast. So things are becoming a little bit more complicated, but it means that this could be my wave that enters in the building, and then the building is shaking and then is released back to the ground. Can we isolate it? Okay, we can try. If we assume that this is my propagation in the underground and this is my propagation in the building, we can calculate synthetic seismogram, and using as a reference the reference on the top, because we know that is the reference that is only showing us upgoing and downgoing waves, is removing, like we have seen before, the effect of the shaking of the building. We can try to see if we take the ratio between the recording in the bottom and the recording on the top, how look like the transfer function for these waves. Which kind of pulse I will recognize describing the propagation of the waves. Okay, I will have a first part that you see, it's simply describing the propagation in the first layer, let's say tau1, and in the second layer, tau2. How much of this wave is propagated? Okay, this depends mainly on the part of energy that is transmitted at this boundary, like we have seen before. Then I can immediately recognize a term in my transfer function, in my or that depends on the energy that I miss due to the trapping, let's say, inside of a structure. I will have a term that is describing the reflection from the free surface. so of the earth. So the wave arrive here, and one part goes in the building and one part is immediately reflected by the ground. I will have an important term that is the wave that reaches the top of the building and from the top of the building is sent back in the ground. And you see is this term, and that's exactly the term that I would like to isolate, because it's the term that is telling me, okay, the building now is sending energy back to the ground. I want to measure this in my real data. Unfortunately, there is another term that has the same time of propagation of this, that is related to the waves which are trapped inside the buildings, let's say. But fortunately, generally for standard, let's say, impedance contrast, since this depends on the square of the reflection coefficient, this term generally is becoming relatively small with respect to the other. So I want to identify in principle this green term. And I see that there is a peak that is really related to it. So I know that the building is sending back energy. So we try to see, with numerical simulation, of course, it's easy. We try to see if we could identify this kind of peak and to separate the wave field that we were recording from earthquakes in all these components. So this is an example of recording in the borough, recording at the surface, and then recording on the building roof. You see how the recordings are different, and you can also see how much their Fourier spectra can look different. In particular, the one on the building roof, due to this oscillation, is very clearly showing at least two, or maybe 3, 4 frequency of oscillation of the buildings. So we apply the convolution again. We use the sensor at the surface as a reference, and we calculate the convolution. If I take the spectrum of the convolution, okay, I see that at the building roof, since it's the autocorrelation, the spectrum will be nearly all flat, apart from frequencies when I will start to filter because the signal to noise ratio is bad. While the other spectra will clearly see trough due to the negative interference of the downgoing waves. And we clearly see trough also well inside the borough. If I look at the same in the time domain and not in the spectral domain, so this is a flat spectrum, Fourier spectrum is giving me a spike. Flatter it is, more spiky it will be, right? Okay, this is my reference in the roof. But I immediately see that I can clearly see some upgoing and downgoing waves and different kind of peaks related probably to some complication in the wave propagation. So now we would like to see, these are examples, if we can recognize these peaks in our seismogram. So you see that the upgoing wave is indicated by orange, and we can clearly follow it. We can identify a peak here in the ground related to the reflection at the surface. And if we follow the propagation up to the roof and down to the ground and then in the underground, we can also follow quite clearly the downgoing wave coming from the building. So this is the pulse that we want to isolate because it's related to the propagation from the top of the roof to the underground. To do this, we made something similar to what I show you for the boroughs. So we can convolve the recording at the surface only for the acausal part of the signal. So if I do this, so I obtain this from the deconvolution. So if I would convolve this with this function, I will obtain again the initial seismogram in the borough. If I will not convolve the one on the top with the whole green function, but only with the acausal part, I will retrieve the part of the input ground motion without the downgoing wave. So I will have a borehole seismogram which is clean by the downgoing effect with a convolution. And therefore, if I do this, I will obtain as input in the borehole this orange seismogram that you see. It's different from the black one because it's not including the downgoing waves. They are removed. So I clean the input from the effect of the downgoing seismogram, or of the downgoing waves. And this was explained also for the boreholes. It's exactly the same approach. Instead of doing a convolution, you can again do it through a deconvolution with using a Landweber filter, but this is a technicality. So even if you don't know what is the structure, you can do it. So in this way, I start from my recording on the top, I correct only for the acausal part, and I calculate the input ground motion at the base. But therefore, if I can do it for the input ground motion, I can also do it for the part of field that is generated by the recording. So if I will take the recording on the roof, you see this very complicated recording, this green one with a lot of oscillation, and I will convolve it only for the part of the green function that is related to the downgoing waves generated by the building, I will obtain a recording at minus 30 meters, which is only considering, you see it here, it's only considering the wave generated by the building and propagating in the underground, which is quite fascinating if you think into it. What is you already notice, you see, this wave generated by the building has a very nice oscillation. And this oscillation is nearly at the frequency of resonance of the building. So the building will start oscillating and will induce, it's like a vibrosize. You can see it in this way, a vibration in the ground, in particular at the frequency of the building. And this we can recognize it even at 30 or even more, in some cases, meter in the underground. So in this way, playing a bit, let me tell it in this simple way, playing a bit with the green function and selecting part of a green function, we can isolate different components of the wave field. We can decompose such a complicated wave field made of upgoing and downgoing waves in some of its components. And one of the components that we isolate here is the one related to the shaking of the structure, which is here. So it's exactly this one, only this one. Interesting, if you compare the spectra then of the Fourier spectra of the input ground motion and of the downgoing wave, what we observe? Exactly what I told you before. So the spectra of a downgoing wave generally it's smaller than the input because the input is also part of the energy that has been released in other waves which are refracted and reflected. But it's very strongly peaked, and it's strongly peaked at the frequencies of the building itself. So the building is releasing this energy at particular frequency, which is its frequency of oscillation. And that's an important point, for example, for Anna Maria. That's why she has to look for this to better identify this in the wave field she is studying. And of course, we can also integrate this spectra in velocity, and since the velocity is proportional to energy, we can calculate also the spectral energy and to see how much is important this amount of shaking released back by the buildings. Okay, once things are working, we decided to test it in different test sites. Here is again the case of Bishkek. We analyze different events, and for all these different events, we made an estimation of the energy of the wave field that was released. We did it in Istanbul for different events where we had boreholes and buildings. And we did it again in Mexico City, where we had also the possibility to study since these recordings were for a long time and also for earthquakes that damaged the building, we could also estimate if there was a change in time of the amount of energy released in the underground. So if you do this, you see these are the recording. It's an example in the borehole, then at the surface, and then in the building. These are the correspondent spectra. You see that the spectra are increasing in amplitude in the underground. We expect this from site effect studies. And there they are becoming very peaked in the buildings due to the resonance frequencies of the buildings. And here you can, from the deconvolution, identify many phases. So the clear upgoing wave, the reflected at the surface, the downgoing wave related to the building structure, and so on. And these are the spectra corresponding to each one of these green functions, where you see this downgoing wave effect with this trough in the spectra are becoming very obvious, not only in the ground, but also in the building structure itself. So if you compare the results for the different situations that we analyze, okay, in Bishkek, we see clearly that not only we have a reflection at the surface, but we have already a reflection of the signal inside the borehole. So it's a stratigraphy effect. So there is a change in velocity in the borehole that is generating a first reflected wave here. Then we have a reflection from the surface, and then the reflection from the top of the building that is propagating here in the underground. In Istanbul, but interesting, you see it down to 150 meters depth. In Istanbul, again, the situation is a little bit more complicated with some reflection at the surface and some complicated signal here. But again, we can follow quite easily also the propagation in the underground due to the buildings. Interesting is what is happening in Mexico City. And it's nice to compare, for example, how the travel time is changing in time on the waves propagating in the building. You see that before the damage, there was some time required for the propagation of upgoing and downgoing wave. Then the building was retrofitted because it was damaged. So you see that there is an increase of stiffness. So the velocity is increasing because the travel time is becoming shorter. After that, the earthquake, the building was again damaged. You see that the travel time is again increasing. But in all the cases, we can recognize a peak, even to large depth, related to the propagation of waves from the top of the building to the underground. And this is what is indicated here in green. So these are just some examples relevant to the effect before. This is the recording at the surface. This is the recording in depth, and they are the corresponding spectra. And this is their input after that it's cleaned by the downgoing waves. You see also how the spectrum is changing. For the downgoing waves, this is the recording at 13 meters depth. And this is the downgoing wave from the building at 145 meters or at 10 meters depth. What you clearly see is that the frequency that you obtain for the downgoing waves in the building is the same frequency peak that you record on the top of the building. So it's exactly what I was telling you before. The building is sending energy in the ground in form of waves that has a frequency very strongly peak close to the frequency of oscillation of the structure. So for all the cases, we could estimate, okay, from the real input, the spectra for the downgoing wave due to the buildings at different depths. And we observe that the amount of energy that is released back in the ground can be significantly different with respect to the input, depending on the situation, especially depending on the impedance contrast between the building and the soil. So for example, at Bishkek, at 10 meters depth, so quite close to the structure, there was still 40–50% of the real input. So the real input, the signal retrieved without the downgoing waves, 40–50% was sent back to the structure. So it's like if the soil is nearly transparent. So this is due to the impedance contrast between structure and soil. This was generally a bit smaller in Istanbul, and again, probably due to the coupling between soil and structure, while in Mexico City, nearly since the soil is very soft, so there was no, let's say, trapping of waves inside the building because the soil is soft, so a lot of waves are propagating down in the ground. So a lot of these waves are propagating, and nearly all the original spectrum of input is sent back then in the earth, to the earth. And this is strongly depending on the impedance contrast. Of course, these are only 3 cases. Would be very interesting in future to have more and more cases in different conditions for different mechanical characteristics of the building of the soil, to see if we can better find a rule, let's say, between amount of seismic input and wave field that is released back in the ground. And I hope that, for example, with Urbesis, we can provide some further hint to this direction, some new knowledge in this direction. So in conclusion, we have made a combined analysis of wave propagation that is done for building and soil structure, and we can identify different phases that can be related to obtained through the deconvolved wave field. We are able to evaluate the real seismic input, so cleaning the input from the downgoing wave effect. But by the way, it's also important if we want to make a dynamic analysis of a structure. You don't want to propagate through the structure something that has also downgoing effect. You want to only propagate something which is propagating upward, otherwise it would be wrong. But very often is not done. And it was possible to estimate the wave field radiated back from the building to the soil and its energy. And this quantity, as I show you, is it's not negligible, so it can be a lot. So the question is if this wave field then can interact with the one coming from other buildings, and if this interaction, like it was shown in numerical simulation, can lead to an increase of shaking or to a decrease of shaking, and therefore maybe to an increase of damage or to a decrease of damage. But for this, we have still to study a lot. Maybe in the future, we will have town with instruments everywhere, and we can better study the propagation of shaking. I have to admit now I'm much more interested in the shaking nearby the surface, not so much in the one in depth. Of course, could be also interesting to have a full view, but I think the priority in this moment is the study of the propagation and in the interaction of waves, let's say between structures in the close to the surface where things are happening, where foundations are, and so on. So I think this will be the big issue for future. So, okay, we had a few experiments also trying to put sensors at the surface, nearby building structure, recording noise. And Anna Maria, for example, is doing this job in different areas. And the idea is to retrieve something from this structure and to understand better if, for example, the different buildings can provide wave field that we see are coming from different structure and how they are interacting. Okay, so that's all by my side. If you have questions, I would be happy to answer.
Yes, I have one question right
Yes.
here. Yes. Okay. I was wondering in terms of the deconvolution operation, the part in which we applied also that operation to estimate the damping, the quality factor. I was wondering of whether or not the deconvolution introduced any type of artifacts in our signal that might be a problem or not to estimate accurate quality factors. I don't know if
No, you're right. I understand what you mean. Anyway, the convolution, whatever you're using, is in some way using some numerical, I can say, regularization of your spectra, no? Or of the results of your spectra. And therefore, this can have some effect on the quality factor. But honestly, I think that the uncertainties that you have anyway in estimating the quality factor, in the case I show you, you are assuming a homogeneous medium. I think the uncertainties related to this assumption are larger than the bias that you can introduce with a well-regularized deconvolution. That's my feeling also from the inversion that I carried out, really using the trough after the deconvolution and the shape of the trough. I don't expect that this is the major issue that you have. The major issue is really the combination of the propagation effect with the intrinsic part of attenuation that are very, very difficult to distinguish. I think that's the major point.
Yes. Okay. So might be considering whether than using a elastic medium, maybe a dissipative medium, sort of.
Yeah, but what do you mean in the modeling of the real data, or in what? Because that's exactly the point. The point is that generally we are estimating a quality factor that is neither, it's a combination. You can call it apparent, if you like. It's a combination of many effects, combining scattering, combining intrinsic part of a quality factor. But the point is that, for example, in the modeling, we use this apparent quality factor as, for example, intrinsic. And this might be a problem.
Yes.
This, in my opinion, that's exactly the problem. Until you use it for modeling in the same way you obtain it with the same model in mind, it's fine. But when you start to use this as something which is not, then you will introduce a large bias in the simulation. This is, for example, happening very often in seismology when you obtain an apparent quality factor and then in numerical simulation or ground motion, you use it as intrinsic.
Yes.
And I mean, the reduction of amplitude in the amplitude spectrum, it's one question, but the effect that, and so you can reproduce this reduction of amplitude over a spectrum, maybe with apparent one, and that's fine. But if you take the apparent one as intrinsic and you try to reproduce time series, this will introduce a large bias, maybe not only on the amplitude of shaking, but especially on the duration, which is very important. And this is really one of the main issues that we have at the moment. But it's a really a big issue. It's not easy to be solved.
Okay. Really nice. Thank you for that.
Okay.
Yes.
If someone is interested, I would like to say, generally, we are also having, especially for the diploma student, we had in the past several theses of a diploma on subjects that we are dealing in the course. One subject that now could be interesting, we are doing inversion of surface waves, especially for gas hydrate. So what you have seen as inversion of dispersion curve we would like to extend it in, so we are doing already, but we would like to extend it to several profiles using the contribution of all the modes. So we are now inverting for large number of modes in order to improve the velocity profile that in turn is used in seismic reflection analysis for exploration. So if someone is interested in doing this could be for sure a subject, but in general I'm also open to any other subject of the course on the analysis of building data, borehole, and so on. So if someone has any curiosity, would like to hear his diploma work on these particular topics, has just to contact me and we can organize it.
Okay,
Yeah.
thank you.
Okay, any question?
I have a question.
Yes.
When you consider propagation between two layers,
I hear you very bad, Dunga.
Okay.
There is a lot of echo.
can you hear me?
Bit better.
Now it's better.
Okay.
Okay. I mean, when you consider wave propagation between two layers,
Yes.
you consider medium is homogeneous or inhomogeneous?
Okay, it depends. In reality, when you do the convolution between two parts, you are always considering this homogeneous in terms of velocity and so on. We made a test also using the results of the convolution for obtaining the characteristic of the medium by inversion. So in the inversion, we were generating theoretical green function for a model, and we were trying to fit them to the observed green function, changing, let's say, the characteristic of the medium. And in this case, maybe you can add something more, but you can add something more in the sense that at least in your green function, you can include the effect also of reflected waves between different layers. So in one step, you can include also a layering in your model. And this is allowing you to improve a little bit the quality of a model, taking into account some inhomogeneities, in this case, only vertical inhomogeneities. Okay?
Yes, thank you, sir.
But of course, if you look at the different direction, so in a building, for example, like I showed you, you can also have instrument places in different position, like we were discussing before. And therefore, you can also account for some lateral variation of the characteristics. If you remember, we had the different velocities, for example, for different installation in different position in the structure.
Yes, yes. Thank you.
You're welcome. So, no other question? Your last chance?
Professor, I have just a small curiosity.
Yes.
With the back propagation because of the buildings, I was wondering what could be the potential consequence that we may see in future, let's say, and then also what would be the how significant it could be, you know?
Yeah, the general dream could be, if we could study this a priori, but it's really a dream, take it as a dream at the moment. Maybe in future we would be able to design an urban area that depending simply on the position of the structure and knowing the underground, it's able to mitigate the shaking. So due to that we can in some way create some negative interference between what is generated by the building in order that we can damp the effect of shaking. So this is a dream, let's say, but this could be really important to study. We know in the past you had some particular damage pattern that probably are related to this positive interference of shaking. So at least we should avoid this if we can. But we are still at the very beginning of this. We have very few empirical data, and we have to rely mainly on numerical simulations with very simplified models or with very simple coupling of building and soil. Now we are developing more and more also on the modeling. So we are working with other groups also in trying to make the numerical simulation more realistic, but it can be done to a certain level because the characteristic of the underground cannot be known so well, especially at this distance range over large areas. I mean, we can do it on a specific site, but can you imagine? So it could be very complicated. So I don't know, that's a bit of a dream. If we can use this information to mitigate damage in future. So in order to find the best solution, at least by the geometrical point of view, for reducing this kind of effect. And we really hope we can do it. But as I said, we are at the very, 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 very beginning of this. It will take a long time. Maybe you will do it.
Let's see. Yeah, thank you.
Okay. So I thank you.
Yeah, Prof.
Yes.
Yeah, I have one thing to say about the exam.
Yes.
I sent the email to the secretary, the diploma office. Yeah, and she said I should let you send her a message to confirm it.
Yeah, I confirm. I said that for me, if there is no problem from ICTP, it's fine. I wrote her yesterday.
Yes, I don't know whether maybe she didn't receive the message.
Why?
So the message came to me, so I don't know.
Really?
Because I received I received a message.
I can check it. Wait. I check immediately. So it should be to diploma, no? Right.
Yes.
Diploma. No. Oh, it's a strange email. Oh, diploma. Oh, no, but it's also, it's sent to diploma. So there are many email addresses. You think she didn't get it? Well, I try again.
So you send it to only email.
I send it only to diploma now, so she should get it. Okay, let's try again. Let's see. Okay. Thank you. Okay. So I want to thank.
Professor.
Yes.
Please, I have last question.
Yes.
How the question will be? How
will be very bad, very difficult, and I will be very happy. It's okay, the answer?
Okay. No, I just wanted to say.
No. Listen, I think you should really try to study. And the important point to me generally is not that you remember everything or whatever. So don't try to learn everything by memory. I don't know how to say in English, but just try to think and to make connections between things. All the things I show you are related, and especially try to think. Maybe you don't remember an equation, but the important point, if you know how to reach it, if you can think, that's the main point. If you have the tools for doing things, that's the most important part of that, not remembering every slide or every photo in your mind. That's a point. That's what I can tell you. Try to think. Take your time and think. Okay?
Okay, thank you. Okay, thank you, Professor. Thanks.
Anyway, if you will have questions before the exam, just contact me. Okay?
Okay.
We'll try to discuss it.
Okay. Okay, thank you.
I will try. It's a difficult period, but I will do my best.
I
promise. Okay?
Yeah, thank you.
You're welcome.
The exam will be oral or written?
Sorry?
And the exam will be oral or written?
Yes, we do it oral. Okay?
Okay.
So I wish you a nice evening.
So we did the exam together with the testing?
We did it last year, so we did it online and it was working.
Okay.
I prefer personally, you know, it's always better, but still for this year we have to consider this situation. Next year will be better. I'm sure. I hope so. Okay, thank everyone, and I think I tried to have a course that was a bit balanced between the diploma student, because are the priority, but also knowing that some people over basis and outside was. I tried to give some more info. I hope it was interesting for you. I hope that you enjoy it. That's an important part. And if anyone, not only the diploma student, has questions, please contact me. Okay.
Thank you very much for such a nice lecture.
Thank you to you for participating.
I personally learned a lot of things from this course.
Okay. Thank you. Okay. Bye-bye to everyone. See you.
Thank you very much, Professor.
Thank you, sir.
Ciao, ciao.
Thank you.
Thank you.
Thank you, Professor, for the lessons.
Thank you.
Ciao. Ciao, ciao.
Bye.
Ciao.
Goodbye, everyone.
Ciao Andres. Ciao. Ciao Maria Aurora.
Ciao, Prof.
Ciao.
Buona continuazione.
Ciao.
Grazie per le lezioni.
Grazie a te. Ciao.
Grazie ancora.
Mohammed.